So fluorescence was first discovered by Sir George Gabriel Stokes in 1852 and was further defined by Professor Alexander Jablonski, and those names will come up again in a few slides' time. And fluorescence can occur when any molecule absorbs a photon of light, so the energy from a photon of light becomes into an excited state and then releases another photon under what's called emission. So it's a three-step process: absorption, excitation, and emission. And these are some examples of different fluorochromes. You can see that they all have very, very different chemical structures. One thing that is clear is that they all have these kind of conjugated bonds structures. And as we'll see in a few slides' time, depending on the structure, that really changes the fluorescence properties of the molecules. Okay, so let's have a look at our fluorochrome in this case, or our fluorophore. It's got the structure that we're expecting. On the right-hand side here, we've got what we call a Jablonski diagram. So what we're looking at is the energy levels and the electrons within this molecule. And at the start, they are what we call in the ground state, so they're not excited in any way. So the first thing that has to happen with fluorescence is a photon comes in and this molecule is absorbing that energy. And that what happens in this case is it goes from the ground state up to what we call an excited state. And you'll see in this diagram there are multiple levels of excitation that this can reach. So at the moment we're excited up to this level here. So that's the molecule sitting at the excited state. What happens is very, very quickly it will transition down to this lowest excited state. And this is something that we'll call the Stokes shift, and I'll reiterate that in a few slides' time as well. So this lasts for a very, very short period of time, so 10 to the minus 15, 10 to the minus 9 seconds. And then finally, the electrons will transition back down to the ground state, and that happens when that energy is released as a photon of light coming back out, so being emitted from the molecule. That brings that back down to the ground state energy. Okay, one of the nice things about these fluorophores is that they can go through multiple cycles of fluorescence. So they can absorb, become excited, emit, absorb, become excited, emit. So this can happen multiple times, which helps us when we actually come to do the microscopy. We can actually get some decent signal. One problem you might find is something that we call photobleaching, where the fluorophore becomes physically damaged in some way, and that actually stops that cycle of being able to absorb and emit photons out. Okay, so this is just an overview. This is the Jablonski diagram again. So again, we've got that three-step process. So the initial excitation of a given energy excites the electrons up to a maximally excited state. There's some relaxation down to a minimally excited state. And then finally the emission occurs. And this emission is happening with a lower energy because there's some energy that's been lost here, which tends to be lost as heat. What this means is if we look at what we call the excitation and emission spectra for a given fluorophore, so in this case, we're looking at enhanced GFP. In blue here, we've got the excitation spectra. These are the wavelengths over which this molecule will absorb that photon of light. And of course, it does it most efficiently at the maximum here, but it will absorb photons at all of these wavelengths. But you'll see when it comes to the emission spectra, so the wavelengths of the light that's being released, that's shifted to the right, and that's because of that energy loss. So this is actually what we call our Stokes shift here. So this is coming from the energy loss during the transitions. Again, photons can be released anywhere across this spectrum. Okay, so this will just kind of reiterate what I've already said. So the excitation spectrum is also known as the absorption spectrum of a molecule. Can occur anywhere across that spectrum, but happens most efficiently at the excitation maximum here. And this becomes really important when we come to set up our microscopy experiments later on. Similarly with the emission spectrum, so again, emission can occur across the entire spectrum, but most emission will occur at that maximum peak. Okay, so as I say, this becomes really important when we come to set up our microscopes. It means we have to try and match our excitation source to the maximum of the excitation spectra for the fluorophore. So we want to excite that as efficiently as possible. It's best to do that at position A here, so you get the maximum amount of emission, rather than exciting it at position E, where we're not going to get very much signal coming back from the fluorophore. As I mentioned, each different molecule which can undergo fluorescence has very different chemical structures, and that produces very different spectral properties. So here are some examples of 6 different fluorophores and their excitation and emission spectra. So the top 3 you can see are fairly standard. They've got a standard kind of Stokes shift gap, whereas this one on the bottom right is a very, very interesting fluorophore. Has a very large Stokes shift between the 2 spectrum. This one here is a very wide excitation spectrum, but a very narrow emission spectrum. And again, this one fairly broad in terms of spectra and also a large Stokes shift. So it's very important before you start your experiments that you understand these properties of your fluorophores that you're using for that experiment. Okay, so just to summarize again on fluorescence and how it occurs. So we're looking at a molecule which is absorbing a photon, producing meaning the electrons within that molecule become excited. So this is our excitation spectrum here. We lose some of the energy within the electrons as heat. That produces our Stokes shift, which means the photon, which is finally released to bring us back down into the ground state, has a longer wavelength than the excitation molecule that would have excited that molecule. Okay, so we've covered 3 kind of key things there about fluorescence. So the excitation wavelength, the emission wavelength, and the Stokes shift. Hopefully that's clear to you guys now. There are a number of other properties that are important to think of when we look at fluorescence molecules. So things like the extinction coefficient, which is basically an absorption coefficient. The quantum yield, so the number of photons that are emitted per photon that's absorbed. The brightness of the molecule, which is the extinction coefficient multiplied by the quantum yield divided by 1,000. The pKa is an interesting one. So that's the acid dissociation constant. Essentially, the fluorophore will fluoresce above that pH value. So some of the fluorophores can be very, very pH sensitive. We mentioned photobleaching. So how stable is that fluorophore? So stability is given as a T-half. So the number of seconds it takes to reduce the signal to half. And then finally, the fluorescence lifetime, which we'll talk about later on in the lecture as well, is the length of time the molecule stays in that excited state.